Welcome to this portion of the Crystal Classroom. Today, the topic we'll discuss is X-ray powder diffraction. This is an extremely essential technique used all across the pharmaceutical industry to identify and characterize samples. However, this one is a bit more complicated than the topics we have touched upon so far. So let me offer a bit of background to begin. The way that light interacts with matter depends upon a number of factors, primarily the relationship between the energy in the light and the states available to the matter. Usually, this will decide if the light can be absorbed or reflected, but these aren't the only options. The energy in particular portion of the spectra is tied to its wavelength. If the wavelength of the light is close to the gaps in the repeating structure, then there is an opportunity for the light to diffract. Diffraction is one of the least common interactions between light and matter. In this scenario, it requires a series of spaces separated by a distance that is relatively similar to the wavelength of light passing through them. A crystal is identified as being a solid with a repeating structure, and the spacing of the nature in crystals is usually measured in angstroms. The light with appropriate wavelength to interact with this spacing happen to be X-rays. This means that every crystal should be able to diffract X-rays. For each distance inside a crystal that repeats, there will be an angle that corresponds to where the diffracted X-ray will be the brightest, determined by a relationship expressed in Bragg's law. For more information, see our future session on single crystal X-ray diffraction.